Today's episode is brought to you by Modern Grower. Modern Grower is your source for time and labor-saving farm tools, such as the Paper Pot Transplanter, Quick Click Seeder, and the Jang Direct Seeder. Turn laborsome tasks into free time with tools by Modern Grower. The long-term carbon storage in soils, is that tiny carbon that microorganisms have the trouble finding that we're talking about? Is that where long-term carbon storage happens in the soil, in that size frame?
Yes, is that tiny carbon compound. It's not the big piece of a leaf that is still in the soil. It's not the big piece of a root that's in the soil. It's that tiny bit of carbon that in most cases is a residue of a microorganism in some form. And it's interesting to muse about that. The product of a microorganism is also the material that remains the longest in the soil. And we typically see that the coarser fractions of half-eaten pieces of leaves, those are the ones that are turning over the fastest, whereas the smallest molecules are turning over the smallest. And that makes only sense. If all of that was in solution, it would be most likely the opposite. But since we're working in the soil, a small molecule that has a lot of oxygen and a lot of different forms and that can hide somewhere in a small pore or adsorb to iron and aluminum in the soil and clay minerals, those small molecules have a lot of options to not be eaten. Whereas a big piece of a leaf, that's a big piece of carbon that is relatively homogeneous at one location. So now, as a microorganism, you just go to town. You can just specialize on that leaf and then eat it all or most of it. But then all the compounds that are made out of that, these smaller molecules that are then swimming away and are unique and absorbed to clays and hiding in a small pore, those are then much harder to eat for other microorganisms. Yeah, so that is definitely the case.
So then if we wanted to increase that store of carbon as humans, the only way we can get more of that microscopic carbon into the soil is by putting more macroscopic carbon into the soil. So the more we can feed into the top of the funnel, the more by default is going to come out the bottom end of the funnel via microbial action.
Yes, that is correct. So adding more to the top of the funnel helps. That means not putting compost in, growing more plants, or not removing less carbon, plant carbon from the soil. That all is a very straightforward way of doing that, but also to reduce the loss on the lower end. So if you extend the funnel a little bit lower and say, okay, well, at the very tip of the funnel is where CO2 comes out, and we're making that funnel very tight, then we can also retain more carbon in that funnel, in that chute. And that is, for instance, as you mentioned before, reducing tillage. Reducing tillage doesn't increase the carbon in, it doesn't put more carbon on top, but it reduces that we lose less carbon at the bottom of the funnel. And so reducing tillage or other soil disturbances is definitely one possibility. Adjusting water contents is another. A very popular topic is to think about wetland restoration in California. If we restore wetlands, we will accrue carbon not because we're putting more carbon into a wetland, but we're losing less carbon through mineralization of that carbon that is in there. So moisture is another good way of regulating the losses and so on. So it's both. It's the input on the top end and the output on the bottom end that will regulate how much is in there in the middle. And the interactions of those two, that is really where we're still experimenting the most on field and farm scale to understand how we can do that. And again, wetland restoration is just one example where one could imagine to increase water levels and increase the water table to an extent that it reduces decomposition of organic matter and at the same time not decreasing productivity or maybe increasing plant productivity. So looking at optimization between more input and less output is really interesting. And because these are not linear, it's not that if you increase double the moisture content in the soil, that also means you're halving the mineralization of carbon. These are all nonlinear relationships, as is the reaction of plant growth above and below roots and shoots to decreasing or increasing moisture in the soil. It's also not linear. And since none of this is linear, it's also not always completely predictable what combinations of all of that will generate. And so those are very interesting discussion points to think through and experiment and find local solutions, because we also know all of this. And this is really where we need just so much more information about local conditions, because all of that changes with, say, texture or mineralogy, or how slopey that land is, or how deep the soil is, or what your rainfall distribution is. And all these local conditions will affect all these factors and might even turn the results on its head. So we need, for optimizing our management, we need all that local information. And it goes to that such a degree that I think many have now understood that we need this view that is at the moment called digital agriculture or digital agronomy, or such terms that recognize that we need really information for almost every meter of the soil, that the farmer needs that information to optimize management for a certain outcome, whether it's crop yield or soil organic matter accrual or lower leaching and better water quality or whatever the management objectives are. We need information almost meter by meter of a field because it changes so much. And while for many of the individual decisions, we probably have a lot of the information at hand, translating that into field scale recommendation requires all these fine points to be translated into variable management over, let's say, a field. And a lot of farmers are doing that already. They know that side of the field, I need to fertilize less. This side of the field, I need to fertilize more. And those kind of things need to be implemented, are being implemented, and farmers are really at the forefront of innovation on these kind of aspects that are figuring this out. And they have known this for forever, right? That you need this field, you need to know your field, and that they need to experiment what works on which kind of field, and translating that into modern tools of management and modern recommendation is really this current step and this current phase that we're in at the moment in soil science and agriculture.
Today's episode is brought to you by Modern Grower. Modern Grower is the go-to source for 100% organic, GMO-free microgreen seeds. Trusted by hundreds of growers for high quality and low prices. If you're growing microgreens, start saving at shop.moderngrower.co.